So, Noether's theorem, part 3. Here we're going to jump right into the theory behind the actual concept of Noether's theorem. So, here it is, Noether's theorem. Every symmetry of the action of a system with a conservative force, i.e. a force in which the work done is independent of the path taken of the particle, has a corresponding conservation law. So in this case, for every continuous symmetry of the Lagrangian, we have a conserved quantity along the trajectories that satisfy our equation. So I here signifies the number of trajectory which it is, from the first trajectory, number 1, to however many trajectories we have, in this case, n. So we're going to define another set of trajectories, which we're going to show are different by the last set by using this dash on top of the Q. But the value of the Lagrangian of these trajectories is going to be the same as the ones we looked at before. So we've got a different set of trajectories but with the same Lagrangian. Given this is the case, a certain transformation has been applied to make the first set of trajectories, Qi, into the second set, Q dash. This transformation is therefore a symmetry of the Lagrangian. So let's just do a little example using these 2 points, T1 and T2. Let's call the action of this trajectory A. If we take these 2 points, as we did in the video a couple sessions ago, and move it to a different place in space, then the whole system is translated in space, but the values of the position of both those points have changed. So the action and the path will still be identical. This represents our symmetry of the Lagrangian. Now let's assume that any small variations causing inaccuracies in our trajectory will not have any noticeable effect of the action. In this case, we can say delta A is 0. When we translate this system from one place to another, the tiny variations are also translated, so delta A is also 0. This means symmetries of L, the Lagrangian, give us these symmetries of the equation of motions. Okay, so when you're ready, just have a little look through section A of the worksheet and try and familiarise yourself with these concepts. Obviously, if you don't understand anything in the slides before, just pop back the video a bit, pause it and have a good look at it, because we'll build upon these concepts later. Okay, so now we have looked at and understood the kind of basic principles behind this, we're going to look a bit more deeply at the mathematics behind these conserved quantities. So let's have a look at spatial translational symmetry first. Now, the total Lagrangian for this system is, as we've looked at before, T minus V, or kinetic energy minus potential energy. Now, because we're looking for the system as a whole, we're going to take T1, which is kinetic energy from number 1, and T2, which is kinetic energy from number 2. And then the same with potential energy. V1 potential energy from 1, V2 potential energy from 2. So x here signifies the position along the x-axis we've got here. And in the last equation, we've got x with a dot above it, which is the differential of x, which is going to equal velocity. So we've essentially got down here half mv squared, which is what t, or kinetic energy, equals. And then we're going to minus from that the potential energy times the difference in location between number 1 and 2. So to show that momentum is conserved, let's let x1 and x2, in this form with the bar above to signify that they're vectors, be trajectories that satisfy the equation of motion. Now let's consider tiny variations within these trajectories. In this case, epsilon t. Okay, so next we find the action, which we discussed is the integral of the Lagrangian. So for the translated trajectories, we're going to include this epsilon term. So if the vector x is stationary, then as we looked at before, delta A is going to equal 0. So we can cancel out that term. So let's now calculate the action, including these epsilon terms. Let's stick with the left side of the equation here and calculate the action. Now, after simplifying, you can see we've got 3 different groups of terms here, essentially, which correspond to our original expression, as colour-coded here. Performing this corresponding integral, which is the second blue part of the expression in the last slide, by integration by parts, this is the answer we achieve. Now, we know that this answer equals 0, so the expression in the brackets must be equal to 0. Now, the expression within these brackets is equal to the change in momentum. In this case, we've shown that momentum is conserved because it doesn't change with time. Here's our expression, and in red we got the change in momentum over time equals 0. So, more generally, we've shown that we've found a symmetry of the Lagrangian for a conserved quantity on a transformed action. Okay, so it's now about time to define the parts of our original statement of Noether's theorem. So we got continuous symmetry, in which symmetry is seen as motions, which we'll explore further in our group theory section of slides. We've got a conserved quantity, which will not change upon some kind of translation. We got a trajectory, which is a path that can be intuitively predicted, and equations of motion, which are those equations which describe the movement of objects. And finally, the Lagrangian, which is the state of the system in terms of kinetic and potential energy. Okay, so now give a crack at section B of the worksheet. Great, so there it is, Noether's theorem. I hope you've enjoyed learning about this concept and have learned something useful and interesting and challenged your thinking about the world. If you enjoyed this series and want to learn more about these extracurricular maths activities, please go over to our website and check out some of the other resources that are coming up.